In this video, we describe at a qualitative level the main types of intermolecular forces that are at play in liquids and solids. Right, there's various types of ways that molecules or particles in a liquid and a solid interact with each other. And they can be separated by the type of particle, the electrostatic properties of that molecule or that particle that is in that liquid and solid. In general, those can be either ions, like for example sodium plus, or they can be dipoles, such as for example HCl, or perhaps they can be apolar, such as N2. Alright, these are the main classes of particles or molecules that you can have in a liquid or a solid according to the electrostatic properties that they have. In an ion you just have a full charge and that tells you whether you have a cation, if this is positive charge, or an anion, negative charge, and so forth. In a dipole, what you actually have is that there are no full charges, but because if it's possible that you can have a difference in electronegativity between the atoms, what that is going to mean is that you have a negative end of this molecule and a positive end of this molecule, and that generates an electrostatic or electronic dipole. Okay? And then in apolar molecules you actually have that there's no either full ions or any permanent dipolar separation of the charge. Right, so what we can do now is study the interactions between these types of species, right? So if you have interaction between two ions, then that will be captured by Coulomb's law, and we're not going to study that here. Okay, we have two positive charges, the interaction between two cations, that will be a repulsion. If the ions have opposite charge, then there will be an attraction, and again that is all governed by Coulomb's law. Right, we're more interested in interactions between dipoles or between substances that are apolar. Alright, so let's think about the interaction between two dipoles, so HCl and HCl. Okay, so the idea here is that because you have a negative end and a positive end, there can be an electrostatic interaction with a neighboring molecule in the liquid HCl. Okay, that would be HCl like this. Right, so notice that the positive end of one of the dipoles is in the line of sight of the negative end of a neighboring dipole, and that establishes a fairly strong intermolecular interaction. Now, this is what we call a dipole-dipole interaction, and we're saying that they're reasonably strong, but they're quite weak compared to a covalent bond. Right, so a typical dipole-dipole interaction, like what you have right here, might be 1% the strength of a covalent bond of the molecules involved. Okay, so again, that intermolecular interaction might be about 1% the strength of that covalent bond. Okay, but that is what we call a dipole-dipole interaction. Now, there's a special type of dipole-dipole interaction which is particularly strong, and that is what we call a hydrogen bond. Right, so it turns that when you have this type of interaction, okay, for X generally being N, oxygen, fluorine, and there are other atoms that are in this list. When this happens, it turns out that this interaction is really strong, and that's what we call a hydrogen bond. It will be much stronger than you would expect from simple dipole-dipole interactions of the same type. That is what we call a hydrogen bond, and this type of interaction is pervasive everywhere. So for example, in liquid water, those are hydrogen bonds, right? So if we can think about how two water molecules would interact with each other, okay, what you actually have is something like this, okay, where this H would be coming out of the plane, this H would be going inside of the plane, and that is a hydrogen bond because of course oxygen is in this list that we have put here as generating hydrogen bonds. And again, what this means is that this confers very interesting properties to the liquids that exhibit these hydrogen bonds. For example, the boiling point of water is unusually high for the low mass of the molecule, okay? And that is all caused by these strong hydrogen bonds. Right, so even though we're saying that these hydrogen bonds are a little stronger than your typical dipole-dipole interaction, they're still not nearly as strong as what you have in a covalent bond, right? So the hydrogen bond in a water dimer is about 25 kJ per mole, and again, that still has to be contrasted with the 480 kJ per mole that you have in a covalent bond within those water molecules, right? So we have studied interactions between dipoles, we have studied interactions between ions, we've said that the hydrogen bond is a special type of dipole-dipole interaction which is unusually strong, and then we still have to see what type of intermolecular forces do you have between molecules that are neither ions, neither have a dipole moment. Okay, so well, the first question that we have to ask is whether those molecules, such as nitrogen, or perhaps we can take now here atoms like argon or helium or xenon, okay, whether those molecules will actually, or those particles will interact at all. We know that the answer is yes, because you can condense all of those gases into liquids. All right, and once you actually have liquids, then those molecules must be interacting, otherwise you would not be able to put them in the liquid phase, right? So there has to be some sort of interaction. The question is, well, how do we understand that interaction? Right, so even though these species are neither ions nor have a permanent dipole moment, okay, they can generate a temporary dipole moment. Okay, so for example, if we take, let's take two argon atoms. Okay, when we look at argon, there's an electronic cloud surrounding that argon atom, and that electronic cloud can be fluctuating. Okay, so on average, you're going to have exactly the same number of electrons or electronic density in any direction around that nucleus. Okay, but temporarily, it is possible that there might be a fluctuation whereby there might be a nexus of electrons in this side of this atom, that in that side, and what that does is it induces a temporary dipole moment. Okay, and then what will happen is that if you have a nearby argon atom, okay, this temporary fluctuation, that temporary dipole moment, okay, is going to induce a temporary dipole moment there, such that there's going to be a bias of electron density towards that end of the molecule. You will be generating there a tiny temporary negative charge, and then you will have here a tiny temporary positive charge, and like that, you now are able to interact. Again, an important difference here is that on average, there's no permanent dipole moment, but these molecules can have a fluctuating, fleeting, temporary dipole, okay, which allows them to interact like this with these fluctuating dipole moments, and this is what we call dispersion. Okay? Dispersion also plays a role because it's part of many molecular interactions in the life sciences, in our bodies, and in many substances as well. Now, something that is important here is to recognize that there is a dependence of the strength of this dispersion interaction and the molecular mass. Right? The ability of atoms or molecules to polarize their electronic clouds to induce these temporary dipole moments is what we call polarizability. So the more polarizable you are, the larger these dipole moments that you can generate. And it turns out the polarizability grows as you go down on the periodic table. So if you take a look at the rare gases, you will have helium, neon, argon, krypton, and xenon. Xenon is the most polarizable of them all. It has a very large electronic cloud that is very diffuse and can be polarized relatively easily, right? So the polarizability is largest for xenon. And what that means is that the intermolecular interactions or interatomic interactions between xenon atoms in liquid xenon are actually much stronger than between helium atoms in liquid helium. And what that means is that it's much easier to form the liquid for xenon than it is for helium. Right, so what we can do here is see what the boiling point of the liquid would be, and then what happens is the boiling point also increases this way. All right, so it's much easier to condense the gas to the liquid for xenon than it is for helium. As a matter of fact, for helium you would need to go to about 4 Kelvin or so under ambient pressure to actually be able to have so little molecular motion, thermal motion, that the very tiny dispersion interactions that you have are able to form the liquid. For xenon, that is actually much simpler, and you can get the liquid temperatures that are much higher. Okay, so in this video we have seen a very qualitative summary of the main types of intermolecular interactions that are at play when you form liquids and solids. Okay, we've seen that those can be classified according to how the electronic properties of the molecules that are forming the liquid or the solid can be codified, right? So if you have ions, there will be ion-ion interaction. That's simply a Coulomb law type of interaction. If you have dipoles, you will have a dipole-dipole type interaction, and we've seen that a hydrogen bond is a special case of dipole-dipole interactions. And then we've also seen that even when you have any type of ions or permanent dipole moments, or most apolar molecules, all apolar molecules or particles can have temporary dipole moments, very fluctuating, very short-lived dipole moments that allow for dispersion interactions, which of course will be much weaker than dipole-dipole interactions or ion-ion interactions, but nonetheless exist and cumulatively can actually add to quite a bit.